hello, Jai Kishan.
Hello, good afternoon, sir.
Good afternoon. So, Jai Kishan, let's start your snap mock for BARC.
Okay, sir.
So, you want some snap for thermodynamics?
Yes, sir.
Okay. Okay. Okay, Jai Kishan, let's start. My first question is to you. What is first law of thermodynamics?
First law of thermodynamics is basically the conservation of energy, and it states that energy can either be created or be destroyed, but can be converted from one form to another.
So, where this first law is applicable? Like it is applicable to reversible process, irreversible, or what?
First law is applicable for all processes,
Whether they are reversible or irreversible.
whether they are reversible or irreversible.
So,
It is
any place where first law is not applicable?
first law have to be applicable everywhere, sir.
Okay, Jekishan, suppose if I will give you some water, like suppose 500 ml water, if I will give you,
Okay.
which is at a temperature 300 Kelvin initially,
Okay, sir.
and suppose we want to boil the water, हम उसको क्या करना चाह रहे हैं, boil करना चाह रहे हैं,
Okay.
and I'm giving you some kind of resistive coil heater, or what you can say kind of hot plate, जो electrical heater होता है ना, so
Okay,
some
sir.
kind of hot plate you are having which is of 1 kilowatt.
Okay.
1 किलोवाट की hot plate है आपके पास, है ना?
Okay.
So can you tell me how much time that process is going to take for heating water, for boiling water?
Sir, can you tell me the temperature of the water again? Initial temperature?
300 Kelvin.
300 Kelvin. That is 27 degrees Celsius. Okay, sir. 1 kilowatt. We usually solve this using heat transfer, sir, because the time is not related, is not studied under thermodynamics. Okay, I will solve it. Okay. 1 kilowatt is equal to 4.18 into okay 73 into T. Sir, 4.18 into 73 divided by 4.18 into
Just show it to me. Just show it to me how you are calculating. Just tell me the all suitable assumptions also. You need to tell me all suitable assumptions, and then you can show me the equation, which particular equation you are using.
Okay, sir. I took the container as a system, and all the heat that is added into the system is converted into the internal energy of the system. And as a result, the temperature of the system rises, and at 100 degrees Celsius, it starts boiling. And I use the equation Q into T is equal to MC delta T.
Just show me the equation now.
Sir.
Put it close to the camera. Fine. Slightly below. So, fine. MCDT.
Yes, sir. C is the specific heat of the water.
So what will be the Q? Q you are taking it as 1 kilowatt.
1 kilowatt. Yes, sir.
Okay. Just tell me, Jay, this particular process is a kind of reversible process or irreversible process?
Sir, in actual sense, it's an irreversible process, but it can be considered as a reversible process.
When it can be considered as reversible?
When we consider that the heat transfer is occurring with the there is no finite temperature difference between. That is, the system and system is in thermal equilibrium. If you consider in that sense, we can say that this is a reversible process. Boiling is an irreversible process, sir.
No, just tell me. You are saying when we are heating it, obviously the hot plate temperature will be different, and the water temperature is going to change.
Yes, sir.
So the temperature difference is there. Obviously, temperature difference is there.
Yes, sir. In a practical sense, there is a temperature difference occurs, but for
So
thermodynamics,
how theoretically it is possible? Like how theoretically you can make this process reversible? Just tell me. Fine, practically fine. Theoretically कैसे आप इसको reversible बना सकते हो? I got your point, Krishan.
okay, sir. The heat transfer occurs through the walls of the container, and
Mhm.
and when we are adding heat to the container, the temperature of the container is rising, and at initial stage, the temperature of the container is equal to the temperature of the water. So the temperature difference between the container and the water.
Let me give you a hint. Heat when you are adding heat from some source, and the system where you are adding it, if they are both at same temperature,
Yes, sir.
means you are adding heat with infinitesimally small temperature difference. You can say the process is reversible.
Yes, sir.
But in this process, what you are adding? You are adding work or heat? What you are adding? In system, what is entering? Means what you are spending? You're spending work or heat?
Yeah. Uh, Sorry, electrical heater you told me, right, sir?
So that electrical heater, what you are giving? You are giving heat or work?
We are giving electrical work, sir.
Electrical work.
Yes, sir.
So work is converting into what? Heat.
Yes, sir.
Whether you are converting it into heat in a very slow manner, fast manner, or in any way. So is it possible to have a such kind of reversible process? Even both temperatures are same, means the coil temperature and the water temperature, suppose you are keeping at same temperature, or means at a very slow rate we are heating water. Okay, at a very slow rate, suppose infinitesimally slowly we are carrying out that heating, then also the process is going to remain irreversible only. Why? Because work is converting into heat. Are you getting idea? Reverse is not possible. Can you get the reverse of that heat into work
Okay, sir.
completely?
Okay, sir. Okay.
Got the point, Jakesh?
Yes, sir.
Acha, just tell me, the process is irreversible. How you are going to calculate the irreversibility in that process? इस process में कितना irreversibility है, कैसे calculate करोगे? Just tell me the irreversibility associated with this process.
Reversibility is usually related to the entropy of the system, and we can calculate the entropy difference during the initial and the final states, and which is proportional to the irreversibility.
So entropy change of the system. With entropy change of the system, you can calculate entropy irreversibility. How?
Irreversibility is
I think Jakesh, I provided you the sufficient data. You know? So you need to try and you need to give me some answer. How you are going to calculate the irreversibility in that process?
Irreversibility is equal to T0 into delta S, where T0 is the temperature of dead set. Here it is 27 degrees Celsius. I'm considering, sir, 27 into delta S, which is MCLN T2 by T1. T2, which is 100 degrees Celsius, and T1, which is the initial state, which is 27 degrees Celsius.
So this is entropy change of system. This is entropy change of surrounding or entropy change of universe. Which you are taking? MCLN T final by T initial. This is what?
This is entropy change of the system.
So that T naught delta S, which we take to calculate the irreversibility, so that delta S is the entropy change of system or entropy change of the universe? Gauss formula equation which you are using, Jakesh.
Yes, I understand. The delta S used in the equation is entropy change of the universe. Since I am not considering any energy interaction outside to the system, heat interaction outside your system. So the entropy change of the surroundings is zero. That's why I am using entropy change of the system in the equation of the reversibility.
Okay. Jackson, what are the reason behind irreversibility? The one reason already you mentioned, the finite temperature difference. But other than that, can you tell me what are the other reasons behind irreversibility?
So irreversibility is of two types, mainly internal irreversibility and external irreversibility. Internal irreversibility is due to friction and also reasons like turbulence and the magnetic effects like that. And the external irreversibility is due to heat transfer.
Jason, my last question is to you.
Yes, sir.
You know, hydrogen and helium.
Yes, sir.
What do you think? Like, suppose if you want to check like how far they are deviating from the ideal gas behavior. So
Sir.
what if there is Z value, the compressibility factor for these gases is greater than 1, less than 1, or equal to 1? And why?
For ideal gas, that is one. And sir, can you repeat the question, sir?
Actually, I asked you for hydrogen and helium gases, which are
Yes, sir.
very, much lighter gases as compared to CO2 or air. So for these gases, the deviation from the real gas will be
Yes.
positive or negative or zero.
Um,
Okay, let me give you a hint. Let me give you a
okay.
hint. You know, Z is nothing but the ratio of V actual by V ideal.
Yes.
So if you know, like for these two gases, the V ideal, V actual will be more than or less than V ideal, you will be able to conclude the compressibility factor. Indirectly, I asked you the compressibility factor or the deviation of these gases will be positive, negative, or zero. Means Z equal to 1 means deviation is not be there.
Not that.
Z greater than 1 means deviation is positive, means Z is greater than 1. Z negative, deviation is there, but Z is negative, negative deviation, what you can say. Okay. So what do you feel? For these gases, Z will be greater than 1 or less than 1? I have given you hint. You can get that idea from V comparative by comparing V actual and V ideal. Jason. Let me provide you two more informations.
Okay, sir.
V ideal you can get easily from ideal gas equation.
Yes.
From V actual, you can follow the van der Waals equation.
Okay. Sir, we assume a real gas to be ideal gas when the the space between the molecules is very large and the volume of the molecule is very small compared to the volume of the container. And with respect to V, sir, variation of temperature P plus A by V square to V minus V is equal to RT. Sir, I cannot say.
One more hint, if I will provide you, Jason, these gases are very much lighter gases.
Yes, sir.
Very much lighter gases. So you can neglect A.
Okay.
You can neglect A.
P into V minus B is equal to RT. And temperature increases.
Actually, when these gases are very much lighter, their intermolecular force of attraction will be negligible.
Yes, sir.
That's why we can neglect that term. So that equation will become, that van der Waals equation will become P into V minus B equal to RT.
RT.
Now try to conclude.
Temperature increases, P minus B also increases, but P is less than P minus B. The volume will be less than that of the ideal gas. So Z will be less than 1, sir.
Less than 1.
Yes, sir.
ठीक है जयकिशन, लेट मी प्रोवाइड यू द फीडबैक नाउ. हाँ,
ओके सर.
तो मैं लास्ट वाले से ही शुरू करता हूँ जयकिशन. हाँ, पहले
ओके.
मेरे ख्याल से लास्ट तक हम एक कंक्लूजन पे पहुंच गए थे कि वी कैन राइट दैट इक्वेशन, वैन डर वाल्स इक्वेशन, एज P into V minus B equal to RT. I think you got the point how actually I am writing this.
Okay, understood, sir.
So this we can write it as, RT
Okay.
plus PV equal to RT plus PV. We can write PV equal to RT plus PV.
PB, okay.
है ना? So if you will divide both side by pressure, so we can write V actual, because that V is nothing but V actual. Yes or no?
Yes, sir.
So V actual equal to RT by P plus B.
Plus B, yes, sir.
And what is that RT by P?
RT by P is
V ideal.
V ideal.
That is V ideal. Yes or no?
Yes, sir.
RT by P is V ideal.
Okay.
So what you are getting? You are getting V actual more than
V ideal.
V ideal. Yes. So that's why if you will check for these curves, actually, अगर आप इन कर्व्स के लिए चेक करोगे, so the float is something like this. कुछ ऐसा होता है फ्लोट, कुछ ऐसा. Irrespective of any pressure, these gases, if you will take at any pressure, like high pressure, low pressure, intermediate pressure, the deviation will be always positive. Are you getting? Yes, चलिए, तो बाकी क्वेश्चन मैंने जो आपसे पूछे थे, I asked you a case of water heating, and I linked some more question with that, like whether that process is reversible or irreversible. तो सोचना है the process is going to remain irreversible because you are converting work into heat, and the conversion of heat into work is not possible. So there must be some net effect is going to remain on the system and surrounding. Yes or no?
Yes,
so the process is going to remain irreversible only.
Yes, sir. Yes, sir.
अगर हीट का ट्रांसफर होगा, मींस इफ यू आर ट्रांसफरिंग हीट फ्रॉम हाई टू लो विद इनफाइनिटेसिमली स्मॉल टेंपरेचर डिफरेंस, देन यू कैन से, बिकॉज उससे उसका अवेलेबिलिटी पे फर्क नहीं पड़ेगा, बिकॉज हीट का अवेलेबल एनर्जी क्या होता है, Q into 1 minus TO by T higher temperature of the heat. So if you are adding heat with infinitesimally small temperature difference, same temperature, then available energy will remain same and the process becomes reversible. But in this case, the process is irreversible only. I asked you about how to calculate irreversibility, so that I think you approached it well. Yes, Jayakishan, I don't know, like you are here or not. I think there is some internet problem. Hello? Hello? Yes, hello, Jayakishan. Okay, Jayakishan, I think there is some internet problem at your side, so you can listen to this later stage. Okay, let me. Yes, Jayakishan.
Sorry, sir, it was a network error, sir.
Okay, not a problem.
Yes, sir.
So I think you got that point. I discussed with you about the irreversibility, why that process is irreversible. Na? We are converting work into heat, so the complete conversion of heat into work is not possible. That's why the process remains irreversible only. Then I asked you about how to calculate that irreversibility. So that you approached it in a right manner. Like irreversibility is nothing but the T naught into delta S generation. But you need to highlight, Jayakishan. Highlight करो थोड़ा सा कि sir irreversibility is nothing but sir loss in the work potential. थोड़ा बताओ ना उसको. So whatever work potential we are losing in a process, that is known as irreversibility. तो अभी work potential दिया कितना, जो हमारे पास हीटर था 1 किलोवाट.
Okay.
अभी कितना हमारे पास हीट है, उसका कितना वर्क पोटेंशियल है, दोनों का जो डिफरेंस होगा, दैट इज नथिंग बट लॉस इन रिवर्सिबिलिटी. जो वाटर है आपके पास, वाटर को आपने बॉइल कर दिया, उसका कुछ ना कुछ क्या होगा, अवेलेबल एनर्जी होगा, एक्सर्जी होगा.
Yes, sir.
So how much energy you invested, expended, minus how much exergy you are utilized, how much exergy you are having. The difference of that is nothing but reversibility. Exergy expended minus exergy utilized. That is reversibility, and that we can write it as Gauss-Todol from Gauss-Todol equation T naught delta S generation. So yes, in this case, because only the work interaction is taking place with the system, between the system and surrounding, there is no heat transfer. So entropy change of the surrounding will be 0, and entropy change of the system we can easily calculate MCL and T final by T initial, you know. So but आपको इसमें एक चीज मेंशन करनी थी कि सर we are boiling, so I'm considering we converted it from like some 27 to 100, means it is in liquid state only, अभी boil नहीं हुआ है. Boil होगा तो then heat transfer and then that you know time required,
latent heat,
irreversibility, that will also be changed. तो latent heat आपने consider नहीं किया तो आपको mention करना था शुरू में. So I'm only assuming sir कि boiling means the water we are getting at 100 degrees Celsius. ठीक है? Okay. Because that is a valid case also. 100 degree Celsius अपने को उसको boil करना था. This just boiling will start, है ना? Steam नहीं बोला था. मैंने ये नहीं बोला था कि steam produce करो. Steam produce करना हो तो then we need to take that. फिर हमें latent heat भी लेना पड़ता. ठीक है? So technically it's right. Okay. I think remaining all questions you answered. First law of thermodynamics I asked you about. I started with that question. तो ठीक है. But थोड़ा सा इसको और interesting बनाना है Jackson. Mention all the I mentioned कि assumption mention करो, then you start mentioning all those things. नहीं तो आपने शुरू कर दिया था. So don't skip the important assumptions. You need to highlight and try to make it more interesting and you know expressive, so that the interviewer or the person who is listening to you, he will show much interest in you, है ना? ठीक है जयकिशन, बाकी ठीक है, मेरे को आपका अप्रोच लगा है. Technically you answered, you tried most of the part. Okay, ठीक है जयकिशन, keep preparing.